Good evening, class. Welcome to assignment number 10, solution session. 10 solution session of NPTEL coursework on electronic theory of solids. So today I'll be talking about the magnetization properties of a class of materials ranging from magnetic properties of materials, based on the quantum mechanical approach and um, the related problems on that. So in today's session you will learn how to approach these kind of problems. If a question is given, how to evaluate the magnetization out of it, the susceptibility out of it, and these parameters. So having said that, I'll start with the very first question, which goes like: if you have an organic molecule has its triplet S is equals to 1, excited states at energy delta above the singlet is equals to 0, ground state, which is the following statement is true. What will, or I can write what will be the what will be the magnetic susceptibility chi for when your kBd temperature is larger than delta, the energy scales, and kBt is also larger than mu b, the splitting part. Okay, so to approach this problem, it's a spin triplet problem. So it can have, for s is equals to 0, sz will be 0, we know. And if s is equals to 1, it can take three quantum number plus 1, minus 1, and the 0. And for them, we'll have to evaluate the energies. So for s is equals to 0, sz is 0, and for s is equals to 1, sz will be plus 1, 0, and minus 1. And then we'll have to write the partition function for these energies, for these spins parts. So if we go to the partition function for this system, so we know the partition function z is written as summation over all energies ei's e to the power minus ei by kbt. Right, that's how we write it. Now let's write the energies for different spins. Right, so if I denote my energies as, this is my S part of energy and this is my SZ part of energy. Right, that's how I denote. So if I write E0 0, that is nothing but mu B, and it will be mu B, right? And in this case your G is 0, so that will give you 0 because there is no spin moment, and if there is no spin moment it's isotropic. In this case, if you apply magnetic field there won't be any difference, right? But for if you have spin 1 as z is equals to -1, it will be delta minus mu b. If it is 1 1, it will be delta plus mu b, right? And if it is 1 0, it will be delta. That's what it's given in the question, right? And an organic molecule has its triplet excited state at energy delta above the singlet. So the difference between this term and this term is delta. That's why we have taken, right? 0 and delta difference will be delta. And then because of the magnetic field, the spin part, it is plus mu b and minus mu b. Yeah. So now we know the energies. Let's put them in the equation 1. Substituting 2 in 1, what we get is z is equals to e to the power 0 plus e to the power minus delta minus mu b by kt plus e to the power minus delta plus mu b by kbt plus e to the power minus delta by kbt. Here mu is Bohr magneton and kb is Boltzmann constant. T is temperature. Now if you use the given constraint, the delta is very less than kbt, and also mu b is also very less than kbt, then in that case, in the scenario, what it will be, e to the power 0 plus roughly e to the power 0 plus roughly e to the power 0 plus e to the power 0, right? And in that case it will be z is equals to 4 if we take this special constraint, right? Now we have the z. Now we have to evaluate the magnetization. So this will be the magnetization, and if we evaluate the magnetization and write it in form of chi h or chi b, this chi will be the magnetic susceptibility. So that's our goal, right? So this magnetization M is given as mu Bohr magnetron divided by partition function z, summation over all spins is as z spin part and multiplied with the energy part is by kbt. That's how you evaluate the magnetization. Right? So you have Hz is equals to 0, then you have plus 1, 0 and minus 1. We'll substitute all of those values, right? And we'll take delta to be very less than kbt, so we'll ignore the delta term for time being. And if you do so, what we get is mu by z, right? And if I break this down, sz0 e to the power 0 plus sz1 e to the power minus mu b by kbt plus sz0 times e to the power 0 plus and then minus 1 e to the power mu b by kbt, right? So if you do so, it will be mu by z exponential minus mu b by kbt minus e to the power mu b by kbt. We know that e to the 4, since mu b is also less than kbt, but we have to estimate the temperature dependence also. So, right, even though it is small, but it will be there. So e to the power x goes as 1 plus x square upon 2 factorial plus x cube upon 3 factorial, right? So we'll take only the first two terms and expand the e to the power mu b by kbt with it respect to it, and then we'll solve the problem. So we do so, m is equals to mu by z e to the power, so this will be 1 minus mu b by kbt minus 1 minus mu b by kbt. Right, and if we do so, what we get is 1 cancels, and m is equals to minus these two. So these two adds to mu square b by z kbt, right? And if we, this is my equation number 3, question number 4, substitute equation 3 and 4, that is z equals to 4, that will give you minus mu square b by kbt to kbt, right? And if we, here is chi, if we write it as m is equals to chi b, and if we compare these equations, chi will be minus mu square by 2 kbt. So essentially your chi is inversely proportional to temperature. magnitude of I is proportional to temperature. So there is the question in which it's a two spin based question with spin s equals to 0 and spin triplet, and in that case the excited state energy of the triplet is also given, and the constraint is given that the kBT is larger than delta and kBT is larger than mu b, and for that we have to evaluate the magnetic susceptibility. So we write first the partition function, estimate the value of the partition function to be 4, and then if we estimate the magnetization to be mu by z times the spin part and the energy part, and if we solve this equation what we get is magnetization goes as minus 2 mu square b by z kbt, where z is the partition function. We substitute the value of the partition functions to be 4, and then what we get is magnetization is minus mu square b by 2 kbt, which gives us a susceptibility which goes as inversely to the temperature. Yeah. So this is the first question. Now moving forward to the second question, which is question number 2. Which of these which of the following option does not show long range magnetic order and have zero net magnetic moment in the absence of a magnetic field? Yeah. First is option A is ferromagnetic materials. B is paramagnetic material. C is antiferromagnetic material. Yeah. So let's analyze the given options. First is the ferromagnetic material, like a permanent magnet. That is ferromagnetic material. Yeah. So if the material is ferromagnetic, in that one the spins will be aligned mostly in one direction. So if let's say magnetic moment of a spin is mu b, and they're aligned like this. Oh, 5, 6, 7, 8, 9, 10, 11, and each of them has mu b magnetic moment. Then in that case, the total magnetic moment will be 11 mu b. Right? And let's define this to be the plus z direction and this to be minus z direction. Right? So first thing to note is that it has long range order. Long range order means the spin which is here at this point and the one which is here at this point, they are aligned in one direction. So they have a order in them. Right? So long range magnetic ordering is there. The second is, so, and the question asks, uh, which does not show long range magnetic order and have zero net magnetic moment. So this one has order, right? So this can't be the answer. Yeah. Now coming to option C first. Let's analyze option C. Antiferromagnet material. So antiferromagnet materials are those in which if one spin is up, the side of it will be down, right? And then up, down. So it means they have zero magnetic moment because the spin cancel each other, but they have a long range order because you can predict what will be the next spin direction. So for example, this will be like this, then adjacent will be down, up, down, up and down, up and down, up and down. Yeah. So that's how it will be. So if this one has magnetic moment mu b, this will be having magnetic moment minus mu b. And in that case, yes, it has long range order. But the net magnetic moment, total magnetic moment will be cancelled by the adjacent spins. Moment will cancel each other. Therefore, zero magnetic moment. Now let's analyze the option B, because the question asks for a system which does not show long range order and have zero net magnetic moment. So now let's analyze the paramagnetic material. So in this one, the spins are oriented. There will be short range magnetic ordering, but after that there will not be any much of the ordering in the spin direction. So paramagnetic materials. So if one spin is up, there will be down, then up, and it can be then up and then down, down and then up, maybe down, up, down, 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 up, up, down. So you can't see any particular ordering in this one. So, but there is a short range order that for this range it's up, for these two it's down, right? So there are short range order, but no long range ordering. Short range magnetic ordering. The- mm, since there is no long range order, material has net zero magnetic moment. Right? So the correct option, if you look, the question asks, is the following option does not show long range magnetic order and has zero magnetic moment. Ferromagnetic has long range order and very large magnetic moment. Antiferromagnet has zero magnetic moment but very long range magnetic ordering, whereas the paramagnetic materials have does not have any long range order. They have only short range order and have zero net magnetic moment. Therefore, only the option B will be the correct response. If there is any question to it, please ask in the chat box or in the comment section. I'll be happy to address that one. Yeah. So if there are no more questions on this one, then I'll move on to the next part of the question, which is question number 3. So the question is that the paramagnetic susceptibility of an atomic gas with number density one point four into 10 raised to power 20 per meter cube in the ground state at temperature T is equals to 400 Kelvin is let me write it to be chi is chi, and the valence electron configuration is valence is the outermost F7. And what is the value of X? Then determine value of X. Now I can give you the constants also. So given parameters, given is magnetic permeability of free space, u naught is equals to 4 pi into 10 power minus 7 Henry meter inverse Bohr magneton mu b 9.27 into 10 power minus 24 ampere meter square. Boltzmann constant Kb is 1.38 into 10 power minus 23 Joule Kelvin inverse. Paramagnetic susceptibility chi is n mu naught mu effective square by 3 kbt with mu effective equals to g mu b under root j plus 1 and g is Lambda-G factor given by g is equals to 3 by 2 plus s plus 1 minus l plus 1 divided by 2j j plus 1. Yeah, so this is about the question. Now let's do the solution. So almost everything is given the question. So depending on the electronic configuration of the F7, we'll have to evaluate the spin and the S and the L part, and then the total J part. We'll then estimate the Lambda-G factor G. We'll substitute this in estimating the mu effective, and if we know the mu effective, we can then estimate the chi, which is the magnetic susceptibility. So having said that, the paramagnetic susceptibility is given as paramagnetic susceptibility chi is given as n mu naught mu effective square by 3 kbt. This is my equation number 1, and given electronic configuration is F7. So your cell is like this with all the sun field of the F, giving S to be 7/2 and L to be 0, and this gives J is equals to L plus S also to be 7/2. So now we know J, L and S. We can estimate the G Lambda-G factor, which is 3 by 2 plus S plus 1 minus L plus 1 by 2j j plus 1. So this L part is 0, so this will be 3 by 2. S is also equals to j, so this will be nothing but 1 by 2. 3 by 2 plus 1 by 2 will be 2. Now Let's label this as equation number 2. Now let's just calculate the mu effective. G mu b under root jj plus 1. G is 2, mu b is 4 magneton, square root of 7 into 9, 7 by 2 plus 7 by 2 plus 1, this will be 9 by 2. So mu effective is nothing but 2 mu b square root of 63 by 2, 2 cancels. Mu effective is mu b times 63. Yeah, this is equation number 3. Substitute equation 3 into equation number 1. Chi is n mu naught mu effective square by 3 kbt. N mu naught mu effective square by 3 kbt. N is nothing but, as in the given the problem, 1.4 in 10 power 20 meter cube. Mu naught is 4 pi into 10 power minus 7. Mu effective is nothing but mu b square times 63, 3 kbt. Kb is 1.38 into 10 power minus 23. Temperature I'll substitute value. And if I substitute the value of mu b square also, mu b is nothing but 9.27 10 power minus 24. So 1.4 into 4 into pi into mu b square is 9.27 into 10 power square into 20 minus 7 minus 48 times 63 divided by 3 into 1.38 into temperature is 400 degrees, 400 Kelvin, times 10 power minus 23. And if you do the math of it, it will get to be roughly around 6 into 10 power minus 11. Yeah. So roughly that number you will get. Yeah. So when to approach this kind of problem, this first you'll have to evaluate the Lambda G factor G. First you'll have to estimate the quantum numbers S, L, and J. If you know the quantum number, you can estimate the Lambda G factor G. Knowing the energy factor G, you can estimate the mu effective, and mu effective is known, K density is known, temperature is known. Then you can estimate the magnetic susceptibility easily using this formula for the paramagnetic materials. Yeah. If you have any question or doubt on this one, please do ask in the comment section or in the chat box. I'll be happy to address that one. Yeah. If there is no question, then I will move on to the next question, which is question number 4. This will be question number 4. The total number of excitations in a ferromagnet is given by an integration over energy. The total number of excitations in a ferromagnet is given by an integration over energy. N is equals to A integral over 0 to infinity dE e to the power half by e to the power beta E energy minus 1, where A is a constant and beta is 1 by kBt. Then how does your total number of excitation in a ferromagnet depends on temperature? Then how does N depends on T? That's the question. So to solve this, already your total number of excitations in ferromagnet is form is also given. So you have to just play with the equation to evaluate uh, the temperature based part of it. So N is A 0 to infinite dE e to the power half by e to the power beta E minus 1. Beta is equals to 1 by kBt. Now let's substitute x is equals to E by kBt. If you do so, you get dE is equals to kBt times dx, and N is equals to A 0 to infinite kBt x kBt to the power half by e to the power x minus 1 times dx. So since this N is equals to A, there is no part in the x of the temperature. We can take out the temperature. T to the power 3 by 2 and Kb to the power also 3 by 2. So A Kb T to the power 3 by 2, 0 to infinite, x to the power half divided by e to the power x minus 1 dx. Since this is a constant number, so the n basically scales as the temperature to the power 3 by 2. This n is the total number of excitations in ferromagnet. So this is your final answer, where n is a portion to t to the power 3 by 2. So if you have any question or doubt on this one, please do ask in the chat box. I'll be happy to address your question or concern. Okay. So if there is no any question, then I'll move on to the next question, which is question number 5. Sorry. Question number 5, which is based on determine the magnetic moment per unit volume of an iron crystal. So the question goes like, the number of atoms per unit volume of an iron crystal is n is equals to 2.5 into 10 power 28 per meter cube, and magnetic moment per iron atom is mu naught is equals to 5.5 mu b, where mu b is Bohr magneton, then the magnetic moment per unit volume of iron crystal is So in the given problem, the carrier density is given and the magnetic moment per iron atom is also given, right? Now the question is asking what is the magnetic moment per unit volume of iron crystal. So it's an easy question which can be easily solved. So carrier density is n is number of atoms. So this is solution part per unit volume. So mu naught is in the given problem is 5.5 times mu b Bohr magneton. Right? So this implies m, which is magnetic moment per unit volume, equals to n times mu naught power 28 times 5.5 times mu b. So m is nothing but 2.5 into and 2.5 into 5.5 is how much? Let me just calculate. 2.5 into 5.5 is 13.75 into mu b is 9.24 10 power minus 24 times 10 power 28. This is 9.24. It's 127.05 into 10 power 4 ampere meter inverse. But in the question, if you see, it asks in the 10 power 6. And so if we just convert it, it will be 1.27 into 10 power 6 ampere meter inverse. So here the answer will be 1.27 for the magnetic moment per unit volume. Yeah, this is how we solve these kind of problems. I think if the time permits, I will take one more question, which is I'll take one more question. The question is, what is the correct expression for heat capacity, or estimate the expression for heat capacity at temperature T of and magnetic moments in a magnetic field H along G direction where each moment having interaction energy mu bh and minus mu bh, where mu b is Bohr magneton. So let's start with the partition function. The partition function is z is sum of s is equals to plus minus 1 e to the power beta mu b and magnetic field h, and let me write hs, so it will be e to the power beta mu bh plus e to the power minus beta mu b h. This is nothing but this gives the partition functions to be 2 cos hyperbolic beta mu b h. Beta is 1 by kbt. Now if you have to estimate the mm, first we have to estimate the mean energy, so that will be mean energy by volume. So its mean energy per unit volume will be minus t ln z by del b, right? And that will, if you solve this, if you take so the derivative of it, you will get the response to be minus n mu bh tan hyperbolic beta mu b h. Now you have this energy per unit volume. So heat capacity is nothing but heat capacity is nothing but C is equals to N del E by del T, and that will be minus N mu B H, or sec hyperbolic sec sec is hyperbolic square mu B H by kBT times mu B H by kBT times 1 by T. So this goes as C is equals to minus T. So the seat capacity goes as N kb mu bh by kbt square sec hyperbolic square mu bh by kbt. So this is the specific heat. Yeah. So given the energy expressions, like how the interaction energies are there, you first calculate the partition function. If you know the partition function, then you can estimate the mean the energy per unit volume to be minus del ln z by del beta. And if, by knowing so, if you take the time derivative of this energy, right, the temperature derivative of this energy, but you will get to be the specific heat, and that's what we have derived in this expression. If you have any question, now I'm open to questions or doubt. If you have any question or doubts, please do ask in the chat box. I'll be happy to address your concerns.
Relative.